This is section 7.4, which involves arc length and surfaces of revolution. In section 7.4, we are given the definition of arc length. And if you want to see the proof of this, which it's completely up to you, if you want to see this proof, you can watch the overview video from section 7.4. Now, and that's in OneNote. So really, the thing that you want to do is find the length of an arc. And in order to do that, you simply use this formula. And just like before, the only difference between these formulas is whether or not the information is in terms of x or in terms of y. So if you're given a function, you need to be able to find the derivative of that function and then square it. That's the most challenging part. So let's take a look at an example. Here it says find the arc length of the graph of a function over the indicated interval. So here we have this function here, 2x to the 3/2 plus 3. Now, this isn't a straight line, so finding the length of this is more challenging, and it involves calculus. Namely, it involves the formula that was given to us on the previous slide, which is s equals the integral from a to b. Here, everything is in terms of x, so we will integrate the square root of 1 plus f prime of x squared dx. So what we need to do is identify what the derivative is. Now remember, y is the same thing as f of x. So we know f of x is this given function. So we need to find the derivative of that. Now, I know it gets confusing going back and forth between derivatives and integrals, and it can be very confusing, but it's something that has to be done, so just go slow and try to remember your steps. So here, remember, I'm going to take this exponent and multiply it by 2, so the derivative ends up being 3x to the 1/2 power because I subtract. Now, if I look at this, the interval that we're interested in is from 1 to 9. I'm sorry, from 0 to 9. So that will be our limits. That will be a to b, our limits of integration. So s is equal to the integral from 0 to 9 of the square root of 1 plus the derivative, which we found to be 3x to the 1/2 power, and this is going to be squared. Now, it's helpful to actually simplify this a little bit more. And we end up getting, now remember, you square the 3 and this exponent, remember, a power to a power you multiply. So this becomes 9x dx. So here, in order to solve this, I would recommend using a u substitution. So in this case, I would let u be 1 plus 9x. So if u is equal to 1 plus 9x, then du is equal to 9 dx. So we do not have the 9, so I will put a 9 here and I will undo it on the outside with the 1/9. So if this is u, then this is du. So we end up with 1/9 times the integral of the square root of u. And remember, the square root of u is the same thing as saying u to the 1/2 power. This here gives us 1/9 times When I add 1, I get 3/2, and then I'll multiply by the reciprocal. And so this becomes 2/27 u to the 3/2. So what I can do is I can replace u and use my limits of integration, which are in terms of x, or I can leave this in terms of u and change my limits of integration so that they are in terms of u. So everything has to be consistent. Now, a lot of the examples I've done, I've replaced it with x, like I put u back in and then use the existing limits that are in terms of x. So let's leave this in terms of u and try it that way this time. So since this is in terms of u, I need to ensure that my limits of integration are also in terms of u. So before, my lower limit was 0. So if I want that to be u, I'll plug 0 in here, and my lower limit becomes 1. My upper limit was an x value of 9. If I want that in terms of u, I plug 9 in here and add 1. So my upper limit in terms of u is 82. So now I'll plug these values in. So I have 2/27 times 82 to the 3/2 power minus 1 to the 3/2 power. I think a decimal approximation here would be just fine. So 54.929 would be the arc length here. In addition to the arc length, we will talk about area of a surface of revolution. So the area of a surface of revolution basically involves the same thing that we had, which was the arc length, or the length of the curve. But then we have an additional twist to this, if you will. So the formula for the area of a surface of revolution is given. And again, it just depends on if we're dealing with x's or y's. But the formula is 2 pi times the integral from a to b of r of x, where r of x is the distance between the graph and the axis of revolution, and the same thing that we had before, the arc length, if you will. So really the only addition is multiplying by 2 pi and by rx. So let's take a look at an example. It says, write and evaluate the definite integral that represents the area of the surface generated by revolving the curve on the indicated interval about the x-axis. So you can see here we're going to take this curve and we are going to revolve it about the x-axis. And what we want to do is we want to find the surface area of that shape. So it's kind of like, I would think of this as one of the cones that you put around an animal's head after they have some sort of surgery. You want to find the surface area of that shape. Okay, I hope you can visualize that now. So let's jot down our formula. Since we are revolving about the x-axis, everything here is going to be in terms of x. So recall, area is equal to 2 pi times the integral from a to b of r of x, where r of x is the distance between the axis of revolution and our curve, times the square root of 1 plus f prime of x squared. Okay, so let's see what we have here. We've already talked about r of x being the distance from the axis of revolution to our curve. So this distance here is r of x. And notice from here to here, this is a y value. This is, if I'm just thinking of the coordinate plane, this is y. And we know that y is 2 root x. So that's helpful. So r of x is 2 root x, or 2 x to the 1/2 power. Now, we also need to find f prime of x, and we know that y is this, so this is the same thing as saying f of x. So that means that f prime of x is equal to, I take the 1/2 down, multiply it by 2, and subtract 1, so that's x to the negative 1/2 power. You can also think of this as 1 over the square root of x, if you'd like. So we pretty much have everything we need for our integral. The only other thing we need are the limits of integration. And if you look at this, our limits of integration are from 4 to 9. So let's go ahead and plug this in. Our surface area will be found by taking 2 pi times the integral from 4 to 9 of r of x, which we found to be 2 root x, times the square root of 1 plus f prime, which is 1 over root x squared. So let's simplify this a little bit. When we do, let's see here. When I square this, so 2 root x times the square root of 1, this becomes just 1 over x, so plus 1 over x. And I want to address a couple things here. Now this 2 is just a constant. This is all multiplication. So this 2 can come out, and I am left with 4 pi on the outside. Okay. Now, if I am multiplying radicals, remember whatever's under the radical, I can multiply the items and leave them under the radical. So I have x times 1, which is x, and x times 1 over x, which is 1. So I end up with the square root of x plus 1. You might want to think of this as the quantity x plus 1 to the 1/2 power. And when you integrate that, remember you add 1 to the exponent, and you end up getting the following. It will be 2/3 times the quantity x plus 1 to the 3/2 power times 1, but that is no big deal, and you'll integrate from 4 to 9. Plugging this in, you will get approximately, make sure you can do this, by the way, approximately 171.258 for the surface area of this cone that would be around your animal's head. That concludes section 7.4.